Hello, my name is Zoe Krauss, and I'm a second-year graduate student at the University of Washington. And today I will be talking about an earthquake catalog that I'm building for the Endeavour segment. But before we get started, I wanted to acknowledge that the work for this project has been done and will continue to be done on the traditional lands of the Duwamish, Lekwungen, Songhees, Esquimalt, and Wasanich peoples. And I wanted to take a second to give gratitude to the land and to those peoples past and present. All right, so where are we in the world? The Endeavour segment is a spreading ridge, a segment of a spreading ridge, the larger Juan de Fuca spreading ridge, off the coast of the Pacific Northwest of North America. And I'm showing here bathymetry overlain by the main tectonic boundaries at the ridge in black lines. And Endeavour is an intermediate rate spreading ridge with a well-imaged axial magma chamber about 2 kilometers beneath these main hydrothermal vent fields here in the center of the ridge. The vent fields are marked by yellow stars. And it's bordered to the north and south by overlapping spreading centers that have propagating tips coming in like this here. And so quite complex tectonics to the north and to the south. And what I'm hoping to investigate with my earthquake catalog is the seafloor spreading cycle at this ridge. And so a spreading cycle such as this is, of course, driven by the accumulation of extensional strain. And with an intermediate spreading rate and a magma chamber, the way that this strain is relieved on the Endeavour is via dike injection. So once accumulation of strain reaches a breaking point, the main magma chamber will inject magma into the normal faults on the ridge, and that will form sheeted dikes, effectively relieving all of the strain along the segment, capping off that seafloor spreading cycle. And then it will repeat itself with the continued accumulation of strain. And that's what I'm hoping, that process is what I'm hoping to study. And if we assume that an average dike has a width of 1 meter, we would expect with 52 millimeters a year of spreading, that cycle to repeat itself approximately every 20 years. And lucky us, we have over 20 years of seismic observations here. And that offers us the unique opportunity to ask the broad question of, throughout an entire spreading cycle, how does seismicity evolve in relation to hydrothermal activity, magmatism, and larger scale tectonic forcing? So the timeline that I'm working with spans from 1995 up until today. And this is the time that I'll be building a cohesive catalog for. So observations start in 1995 with just a 2-month 15 ocean bottom seismometer deployment. There was a bit of a break in observation, and then a 3-year 8 OBS deployment that measured over 37,000 earthquakes in that red time span there. And then in 2012, Ocean Networks Canada installed a cabled array at the ridge, which means we get real-time data. Unfortunately, only one instrument was deployed from 2012 to 2016, but the network was expanded in 2016, and since then we've measured over 38,000 earthquakes. So those colored bars are where we have seismic observations. But where do we know that we are in terms of the seafloor spreading cycle? So we know that dike emplacement swarms occurred on the ridge in these 3 time periods. And so the first one, in 1999, the central segment underwent a dike emplacement swarm. The next one got the southern segment, and the dike emplacement swarm kind of capped off in 2005 with swarms on the northern segment. And so those 3 events together are thought to have relieved all extensional strain on the ridge. And it has been building up since then. So sometime in the future, we hope to observe the subsequent future swarm. And so as I build this catalog, I want to keep my scientific questions in mind to make sure that I'm building the catalog specifically to be able to confidently answer them. And these questions fall under the umbrella of spatial and temporal. For example, are the spatial seismicity patterns consistent only with magmatic inflation and hydrothermal activity in the center of the ridge? Or is there a lot of off-axis activity that gives evidence for tectonic extension? Do we see a lot of seismicity associated with those overlapping spreading centers to the north and south? And even down to the resolution of individual hydrothermal vent fields, can we relate changes in seismicity to changes in temperature or changes in fluid flow? And also throughout time, how does the background seismicity rate evolve between these dike emplacement swarms? Is it linear, or does it happen more in bursts, the increase in seismicity? And does sensitivity to tidal triggering increase as the seismicity rate changes, as extension is continued to accumulate? These are all the questions that we want to make sure we can answer. And in order to do that, we will need accurate high resolution earthquake locations, of course, but also a method to normalize those earthquake counts throughout time, because we have so many different changes in network configurations. If you think back to that timeline and all those breaks in observations. All right, so the first thing I'm going to talk about is how I'm ensuring high resolution locations. So at Endeavour, we are lucky to have a recent segment scale tomographic experiment that gave us really high resolution 3-dimensional velocity models. So I have both a P and S wave velocity model with 0.2 kilometers grid spacing. And what I'm showing here is a map plan of those models cut at 2 kilometers depth. And you can immediately see just how complex the velocity structure is at this ridge. So the main ridge structure is running right down through here. I've left on the markings of the hydrothermal vent fields to give you a sense of direction. But yeah, we see relatively slower velocities associated with these overlapping spreading centers, as those propagating tips cause a lot of fracturing and damage to the rock, and relatively faster velocities towards the center of the segment. And so this complicated velocity structure, it's really great that we can capture all of that detail to ensure that we are using all of that detail in our locations. And because we have only 0.2 kilometers grid spacing, this necessitates an efficient grid searching algorithm. And so I have been using non-lin-loc to calculate my locations. And so we can tell how much these 3D velocity models improve our locations by comparing to locations made with only a 1-dimensional velocity model. So what I'm showing here is all 37 earthquakes located between 2003 and 2006. So this involves earthquakes before the last swarm and also after. And so I'm just coloring by that. And this is a lot to look at, but what is the emphasis here is how improved the locations are with the 3D velocity model. So that's what I'm going to plot next. And immediately you can see how much better the alignment is along this ridge axis here, the improved agreement to geologic features. A lot of the locations made up in here have been brought down and consolidated further south, better agreeing with the West Valley propagator tip. Also with the Cobb propagator tip to the south here. A lot of these distal locations are now aligning much better along the ridge, and other consolidated earthquake swarms, both on and off axis. So we feel pretty good about these locations. They appear to be quite robust. And I also want to point out that thinking back to those spatial questions, we definitely see both on and off axis seismicity. Seismicity is not just limited to these vent fields here. We also have a lot of activity in both of the propagator tips, and also above the vent fields and off flank. And these patterns of seismicity have remained decently consistent up through today. So if we look at the past 4 years of observations from the Ocean Networks Canada cabled array, we continue to see, of course, a lot of activity in the vent fields, but also a lot of activity on the eastern and western flanks, and associated with these propagating tips coming down through here and also coming up through here. All right, so we are getting all those earthquake locations. But how are we going to normalize those rates throughout time and account for different network configurations? So to kind of drive home just how complicated these network configuration changes can be, if we look at just the past 4 years of data from the Ocean Networks Canada cabled array, and these are the 5 different stations we've had, we at all times have had at least 3 stations, but the combination of stations we've had has changed significantly throughout this time period. And so every time we have a different combination of stations, we expect to have a different detection capability. And so we need to make sure that if we are making comparisons across time, we aren't comparing apples to oranges. And the best way to do that is to use magnitudes of completeness. And so if we calculate the magnitude of completeness for all those different time periods, we can just compare earthquakes that are larger than that completeness magnitude and make sure that we're not missing anything. So here's an example B-value plot for just the vent field section running for the time period when we only had an accelerometer for the center station. And for the vent fields, we're measuring a rather high B-value, as you might expect for vent fields dominated by small earthquakes, and estimating a magnitude of completeness, conservative estimate, around 0.9. And so we're still working on getting that estimate for all time periods. But if we conservatively say that we're measuring in the vent fields all earthquakes above magnitude 1, we can compare that earthquake count through time and see how it's changing. And so here you can see that our numbers of earthquakes throughout time isn't really changing much over these last 4 years. We don't see an obvious pattern of increase that maybe we would expect with in continued accumulation of extensional strain. Rather, it seems quite consistent, even getting a little bit quiet in these last 2 years. Another way to look at this is the cumulative moment release throughout time. And again, it seems rather consistent. This is a roughly linear relationship. But we can compare this moment release rate to what it was back in 2005, before the last dike emplacement swarm, so before extensional strain was relieved. And that rate was about twice what we're seeing today. So we definitely aren't up to the seismicity level that was happening before that last swarm. But after that last swarm, the seismicity rate dropped significantly after that strain was relieved. And in 2005, right after that last swarm, the moment release rate was about half what we're seeing today. So we definitely do see an increase in background seismicity since then, but we aren't quite up to what it was right before the last event. And so these preliminary results begin to give us a picture of where we are in the spreading cycle and what that accumulation of strain looks like. And in terms of spatial conclusions, we see relatively consistent patterns throughout time, with, of course, most of the seismicity occurring in the vent field sections, but also a lot of seismicity occurring to the north and the south, likely associated with those propagating tips. And throughout time, we don't see an obvious increase in the last 4 years, but we do see a increase since 2005, since that last dike emplacement swarm. And so there's some future work to be done to complete this catalog and make more analyses of those questions, including resolving the single station observation period from 2012 to 2016, continuing to calculate magnitudes of completeness, and making comparisons across all 20 years of the catalog, and also making an online near real-time catalog to share. And so in terms of the single station observation period, we will be able to resolve ranges to earthquakes during that period, but not full locations. I've done a lot of work trying different methods of first arrival polarization to get azimuths to earthquakes using just one station. But the scattering at this ridge is just too complicated to do that reliably. And this is actually a common problem for mid-ocean ridges. But we will be able to get earthquake count and ranges to earthquakes and be able to add in those 4 years worth of data. And for the online catalog, I'm hoping to have earthquake location files, event histograms, and of course, location maps available for both viewing and download. So yeah, we have a lot of data for the Endeavour, and what we're starting to see is that, yes, there's hydrothermal and magmatic component seismicity, but it's a lot more complicated than that. There's likely some components related to these overlapping spreading centers with their propagating tips coming up through here. And we see a lot of off-axis seismicity, a lot of things going on. And although we don't see that increase in seismicity the last 4 years, we know that our background seismicity has increased since that last diking event, and we do expect that it will continue to do so. And hopefully we will be able to measure a subsequent diking event in the future. So yeah, that's what I have. Thanks for coming and tuning in. My Q&A session is on December 16th. But also feel free to reach out to me personally with questions. That's my email. So thank you so much.